Hi, I'm Murch. I'm going to talk a little bit about some general ideas about wallets and specifically some open pull requests and work in progress for Bitcoin Core Wallet. And I hope that I'll get through all my slides, but please do feel free to ask questions or comment in between. So we'll try to make this a little more interactive. Cool. So what I got for you today is I want to talk a little bit about why we have a wallet in Bitcoin Core, some general best practices in wallet. Are any wallet designers or implementers here, people working on wallets? Yeah, cool. Yeah, okay. I expect you all to promptly implement all these wishes that I have, okay? And then I have a couple newish features that Bitcoin Core has. I'll talk very briefly about the simulations we use to convince ourselves that what we're doing is improving situations. And yeah, then hopefully going to talk specifically about the things that I work on in Bitcoin Core recently. So, why do we have a wallet in Bitcoin Core in the first place? Well, it turns out back when Bitcoin was released, it was the only piece of software that implemented Bitcoin, and you kind of had to have a wallet in order to build transactions. So it literally was mostly in main.h and main.cpp, and you could just build some transactions there. Over time, the Bitcoin Core codebase has gotten a lot more modular, and it's like has its whole own directory and a lot of tests and more functionality since. But what we kind of want to get into especially is we want to show off some things you can do with wallets that maybe more end-user focused wallets or enterprise focused wallets don't necessarily implement right away. We want to showcase a few best practices, and it should still be reasonably usable even though most people run Bitcoin Core for the full node capability, not necessarily for the wallet. Also, we don't really know anything about our user base because we only learn that people are using it when they have issues and tell us about that. So we're all flying pretty blind here. So I have one example here where somebody did ask about something the wallet was doing. So this is a small enterprise getting a lot of really tiny deposits into the wallet and then also making payments. And so they were like, hey, we occasionally get just these huge transactions with lots of inputs, and it doesn't happen that often, but every once in a while it happens. And this one time, it was at 46 satoshis per rebyte, and it used 856 inputs, even though I had a single input that was slightly larger than the target. So that cost me 36 millibitcoin, which at that time was something like $700 or so. So what am I doing wrong? Well, dear user, you're not doing a lot of things wrong. The Bitcoin Core wallet just, at that point, didn't optimize very well for high fee rates, and especially fluctuating fee rates, and it was optimizing for the smallest change output. And that happened to be when you combine 856 inputs instead of the one that was slightly larger. Yeah, anyway, we'll get back to that example a little later. The idea here that I want to convey is it's easy to know when the wallet is doing something stupid, but it's sometimes pretty hard to know whether the wallet is doing something well. And like as a human, sometimes we have an intuition about that, and we would do it differently, right? Fees are fairly high, so I'll pick that single input, obviously, here. But if you want to automate all that, it might be different what you wanted, or it might be hard to cast it into fixed programmatic rules of how to do this. So a few things that the Bitcoin Core wallet has that other wallets might not have implemented yet. I think some of you might have heard of wallet descriptors at this point. This is just a different way of describing all the addresses in a wallet. So previously to wallet descriptors, when the Bitcoin Core wallet had a key, it would generate all the script pub keys that it could derive with one private key. So you'll have a legacy, a wrapped SegWit, a native SegWit, and a page taproot script pub key that it'll look for. So every single time you have a key, it looks for all four things. With wallet descriptors, it tells you how to derive all the keys, what script it's using, and also the derivation path. So, for example, a lot of you will be familiar with the seed phrases for backups, and they don't tell you what the derivation path is. So a bunch of wallets implement the same seed phrases, but then they use different derivation path from the master secret, and you actually have to search all of them when you recover if you don't know which wallet generated the seed phrase, because you might otherwise never see the funds. So wallet descriptors make that better in that it tells you explicitly where to find the corresponding addresses of the wallet. PSBT is partially signed Bitcoin transactions. I think this will be important to use air-gapped and watch-only wallets better. And it also is helpful in making multi-user transactions. So if you want to do a coin join or things like that, you'll use sort of it's a standard for sharing not complete transactions. And a bunch of hardware wallets especially have implemented that, but also as more other wallets implement that, we will be able to create transactions together between the Bitcoin Core wallet and whatever other wallets, because it's a standard. HWI is the hardware wallet interface. We can plug in a bunch of hardware wallets and use Bitcoin Core just as the watch-only wallet and then sign on the hardware device. This one is a little more nifty. So when you accidentally or on purpose reuse addresses, what does that do to your privacy? Okay, yes, I see. I see you have an understanding of this. What if somebody sends you funds to an address you've used before, especially like tiny amounts, tries to force address reuse, or the Bitcoin Core wallet will do two things. If you have not spent from this address before, it will opportunistically try to build input sets that avoid partial spending of inputs. So if you have, say, two UTXOs that share the same address, it'll only try to spend those two together or not at all. And you can even set it to more strict criteria where it will never reuse an address unless you manually override. So if you receive funds to an address again, it'll just ignore those funds until, yes? Until you manually spend them. Yeah?
Payments are only defined by the address you give the payer, right?
Well, since receiving is completely passive in Bitcoin, you can't really control when somebody just sends you some tiny output to an address you've had before. So they can sort of introduce another UTXO to your wallet on an address you used before. So yeah, if you're in a regular, honest sender receiver relationship, then you give the address that you want to receive the payment to, and you'll only expect funds to arrive there. But if somebody's dusting you or stuff like that, you might not be able to control it.
So the phrase there is called dusting someone?
Well, the more correct phrase is forced address reuse. Dusting is sort of, yeah, people talk of dust attacks, but it's sort of not always correct. For example, around the Sochi Olympics, there was this one Satoshi outputs being dusted on a lot of addresses, where people were leaving, I think it was up return messages that were advertising something. And so then it would also be dust at that point, but yeah, the correct term is forced address reuse.
What does APS stand for?
Avoid partial spend. Yeah. All right. Pay to Taproot, I think everybody's heard about a lot. On Bitcoin Core, you can actually use Pay to Taproot already. I think it'll take a while for the ecosystem to catch up and be able to send to it, but I also have a section later making 3 arguments why we all should use more Pay to Taproot. And yeah, automated coin selection. Some wallets have, well, ours could be better, but some people have even worse coin selections. We're working on it. I think that some wallets have pretty good coin selection, but we've also in the past seen very bad coin selection that really ground the wallet to dust and things like that. So there's actually a lot of room for improvement in a lot of wallets on this. Okay. So here's my wish list. Every wallet should do low R grinding. Who knows what low R grinding is? All right, that's a few of you. So signatures in Bitcoin have two values, R and S value. S is always in the lower half of the curve because we have declared high S signatures standard. You can see that up here in the front. So it all started out 25%, 25%, 25%, and 25% down here. And then people stopped doing high S signatures. So the yellow stuff here disappeared. Also, thank you, Timo, for the charts. He runs transactionfee.info. And sorry for outing you. Here, what you see in the back here is people starting to repeat signatures a few times until they get a low R signature. And why would they do this? The encoding we use for signatures, the DER encoding, it adds another byte if you are in the upper half of the curve. So if you have a high R signature, the R value is 33 bytes instead of 32 bytes, and you actually have to pay for a byte more. And it's a fingerprint, right? If you see a wallet or see a transaction where about half of the signatures are high R and half of them are low R, you know it's not a Bitcoin Core signature, for example. You know it's not an Electrum signature because Electrum also does low R grinding. So the idea is here, just repeat signatures until they are low R. It'll make it easier to estimate the fees for the transaction because the transaction is always the same size, and it'll remove that fingerprint. Well, right now it might be more of a fingerprint for Bitcoin Core and Electrum that always has low R signatures, but if everybody does it, we all save. Also not a problem after Taproot because Taproot uses Schnorr signatures and the signatures are always the same size there.
Thank goodness.
Yeah.
Started grinding hard.
Oh, this is the fourth argument why you should do Taproot. Who knows this one? Yeah, you know everything. Okay, so in the far, far future, when the block subsidy has receded to a level where it doesn't really pay for the miners will rely on transaction fees for their revenue. And sometimes, right after finding a block, there might not be a lot of transactions waiting, so it might be more opportune to attack the previous block and try to rebuild that block, include some of the transactions that are waiting plus the juiciest from the previous block, and mine a different chain tip instead, and then try to get a second block to reorg it out. And what we do in Bitcoin Core is we lock our transactions to the next block in 99% of the cases. Otherwise, we use a block, I think, up to 100 before, so that if people build transactions offline, they can have a little noise to hide in. And so the transactions built by Bitcoin Core will only be available in the next block, and they will reduce the reason to do such a chain tip attack. So please lock your transactions to the next height. Yes, sir?
What kind of lock is that? Time lock?
Yeah, we just do a block height-based time lock, and we lock it to the current height, which means that you can broadcast it right now, but it can only be included in the next block.
Also fingerprint.
Yes, also a fingerprint. So if you wanted to find out which transactions were built by Bitcoin Core, what would we be doing right now? Well, we would be looking for a transaction that has only low R signatures and that has a lock time, a height-based lock time, usually to the block that was found, that it was included in. Yeah, and then you might get a pretty decent upper bound on how many Bitcoin Core transactions there are.
But also Electrum does the same, so.
Yeah. Yeah, good citizen, Electrum. So, I think I touched on this already. I just don't get it. Why the hell do we have 53% of the addresses that receive funds reused? Like, this is the worst privacy leak overall because every time you do it, it is completely obvious the same owner of the funds is involved.
I mean,
Yes.
a lot of it is exchanges.
Yes,
That
yes.
You sign up, make an account, they give you a new address, but
Right.
then you want to keep depositing and withdrawing. So
Right.
what you have is that, and if you want to get a new one, the customer support guy has to give you a new one, and he's too busy. So
Right. So my ask would be, or you wanted
Yeah,
to
it's
say,
also drug dealers.
drug dealers.
Okay.
And
Okay.
like, and people who like it's bad, but it's like my buddies are like buying weed and it's always the same address.
Yeah.
Oh man.
You look at, like, fucking tens of thousands of transactions
Yeah.
on this one. It's
Yeah.
really silly.
That's ridiculous, especially in this case where you actually want privacy. Yes.
The other side of those, the other corner of that trifecta of evil between exchanges, drug dealers, and also the pools. So we can only pay out to a single address, and that's very common across all.
Right. So I should repeat for the stream because people can't hear. So somebody chimed in and said drug dealers actually do a lot of address reuse, and that was why we were all laughing. And the other one is that a lot of services have a stored address for the user where they make out their payouts to. And so one way that could be improved is by having a wallet descriptor from the user, where then the service always generates a new address from this wallet descriptor to send to it. And of course the infrastructure or the service has to make that update first. But they're not necessarily financially incentivized to do that.
Soon.
Soon. Should I quote you on that? No, okay. Cool. So yeah, if you build a new wallet or work on a wallet, it would be great if you kept in mind that addresses should really be named invoice identifiers and should be only used once. And you should design your wallet flows in a way that puts the user in the position that he wants to use a new address every single time they give it out. Maybe, or usually also even if they interact with the same counterparty. Cool. We touched on that a little bit already, but there's 3 good reasons why you should use Pay-to-Taproot. So Pay-to-Taproot has been active on, or Taproot has been active on the network since November, and currently we see about 1,000 outputs per day, which is not a lot because we have about 700,000 outputs created per day. So I'll make 3 arguments. One is privacy. If there's more outputs that go to Pay-to-Taproot outputs, they all look the same. Whether they're under the hood multi-sig, whether they use music in their key path, whether they later reveal that there were some leaf scripts hidden in it and reveal some more complex spending conditions and use those. Yes?
I think your mic turned off.
My mic turned off.
Yeah.
I heard it too.
I don't want to say anything, but
Yeah, okay.
yeah, your mic's off. Stream's good.
Okay. I think it's this one that's off.
Maybe just the speaker, but maybe it's still going to
Yeah,
the screen.
I think it's
Still goes.
Okay, all right. I shall try to raise my voice a little more. Can you all hear me? All right? Yeah. Okay, cool. So multi-sig and single-sig is going to be indistinguishable, although some of them might reveal that they're multi-sig later when they spend a leaf script. You get basically for free a way to hide a recovery option or to have a path for your errors in each of your outputs. Right? You can have a leaf script in your Pay-to-Taproot address where, say, you have a 3 of 5 multi-sig with your 5 errors, and you put the wallet descriptor in your will. And then later they have the keys already maybe, and later they can find all your UTXOs with that. And you have it just hidden in your Pay-to-Taproot output, and meanwhile you're using single-sig key path spends all along. But whenever, like, you don't have to respend everything back to a special address so that they'll later have access. No, you can just have it hidden in there for free, carry it along. Stuff like that I think will be more common as people think about what cool stuff they can build with Pay-to-Taproot. And as more of us use it, I think nobody will be able to tell which ones have these hidden nifty backup recovery scripts or all that stuff. And then I often hear, well, Pay-to-Witness public key hash, native SegWit single sig, version 0, is slightly smaller in the round trip than Pay-to-Taproot. right? So as you can see, 68 plus 31 is 99 V-bytes, whereas pay to taproot is 100.5 V-bytes. And why would you still want to do pay to taproot? Well, you're the receiver, right? So the sender pays for the output, and the receiver pays for the input. The input on pay to taproot is smaller. So senders are already all right with sending to my pay to witness script hash address. So they should also be all right to send to my pay to taproot address. But I pay later less. So just from a greedy user perspective, you want people to send to your pay to taproot address in order to save money. So I think that there will be an economic incentive for people to converge on pay to taproot, which will bring us back to the part in the first point where a lot of the outputs will start looking the same and indistinguishable. Cool. Any questions so far? Yes?
Do you think if people use multi-sig today, they're compatible with Frost thresholds later?
So I know of one service that's rolled out latent multisig support already in their key path with music. And they're currently only allowing the leaf script, though, because music wasn't standardized when they rolled it out. But basically, they already spend all their UTXOs to addresses, or at least all their pay to taproot UTXOs, that they can later do music. So you can sort of, if you know already what it will look like, you can sort of build it in already. I'm not up to date on the latest with Frost, how far it is along. I know the spec is, I think, now done. There's another proposal by Tim Ruffing et al. To do it more practically, but I don't know.
Roast one?
Yes, the roast one. Yeah, we had it just dropped 2 weeks ago, I think, right? All right. How am I in time? Okay. Wow. All right, so how do we convince ourselves that what we're doing with our wallets is an improvement? Because wallets are trying to optimize for a bunch of things. I don't want my UTXO pool to be split up too much. I don't want to have like thousands of pieces of Bitcoin. But I also don't want to have a single piece of Bitcoin, because when I spend it, I tell my counterparty how much money I have at least, and all of my money is in flight in the change output. So obviously we want somewhere in the middle for that. We want to have some different output types potentially, and so forth. So there's a very high-dimensional space of things wallets can behave like and do. So how do we convince ourselves that what we're doing is improving their overall situation? So especially Andrew Chow and some other people by now have been working on a simulation for the Bitcoin Core wallet, which essentially is a functional test that has been modified a bit. And it spins up two nodes. One is the tested wallet, and the other one is just let's say the world node. And for the deposits, the world node sends to the tested wallet, and then the tested wallet builds the transactions that we're actually interested in. So we can feed the simulator a sequence of amounts, which is just the payment, positive being deposits, and we zip that with fee rates. So we can have different fee rate scenarios, like, for example, the situation since last year, where suddenly in June, nobody had, or block space demand basically was no longer there, and we almost every day cleared the mempool. And before that, we had 6.5 months when the mempool was constantly backlogged. So we can now simulate under the same payment sequences under different fee rates. And recently, another contributor included that we can also send to different output types. So we can simulate the transition of a wallet between native SegWit to pay to taproot, or all the way from legacy forth. And now we can run a bunch of these simulations in order to convince ourselves, well, costs go down, UTXO pool didn't explode up to unbearable numbers, and things like that. So we have been using the trace points that Timo introduced to Bitcoin Core to glean basically what coin selection algorithm was used in the wallet and what the exact details of the picked input set was. So an example of where that came in handy is there was a pull request 24752, which came out of Circ telling me that the branch and bound changeless window. Okay, I have to explain that a little more probably. There's one algorithm in Bitcoin Core where we try to explicitly find an input set that will not require a change. So if you have a lot of pieces of Bitcoin, you might be able to combine them in a way that you pick, I don't know, the 15th and the 20th, and it's exactly the amount that you need to send your transaction. So you just send to the recipient and you never create a change output. And this algorithm we use basically searches the whole combination space in an efficient manner to try and see if there's such a combination. And since you hardly ever would get that correct to the Satoshi, we allow a few Satoshis excess in order to say, well, this excess of a few Satoshis is less than the cost of creating a change output. So it's going to be more efficient to still not create a change output and just drop those sats to fees. So Circ told me last year that the window in which we accept a changeless input set is too small. So we simulated that. And what you see here is the resulting, there's 3 algorithms right now: knapsack, single random draw, and branch and bound, where branch and bound is the one that creates a changeless solution. The baseline is here on the left. And in our simulations of the baseline behavior, we had somewhere between 40 and 50% of changeless transactions for our scenario. And single random draw over the course of the 5,005 payments we did was somewhere between, lower 30%. And knapsack, which is the horrible, horrible coin selection that's been in Bitcoin Core since 2011 and that I'm trying to get rid of, was not being used all that much. It's like 20%. So what would you think happens if you increase the size in which you accept BNB solutions? You'd expect more BNB solutions. But what happened instead was the yellow curve down here actually is just above 30% now. And we actually got a lot more single random draw solutions, which went to over 45%. And knapsack also increased to almost 25%. Now, that was not what we were expecting. We were expecting that we would get more branch and bound solution, avoid change more often, and save costs. But we did have just a completely different outcome. And this is the sort of thing why sometimes simulating a complex system where previous iterations depend, later iterations depend on previous outcomes, you don't have an intuition for that. So we have this simulation framework now to check whether we're actually improving things. Yes?
So the reason that you don't have intuition on it has to do with the results of having many transactions that are crafted in this way, downstream effects of that?
Yeah, so the scenario specifically has 15,000 payment operations. It does 5,000 payments and receives 10,000 deposits roughly. And so what happened here was that presumably the branch and bound window being a little bigger caused it to use more UTXOs quickly. And then the overall UTXO pool was smaller, which meant that the combination space to find branch and bound solutions was smaller, and we got fewer branch and bound solutions overall, which then caused more random solutions to be used. Something like that. We have the data, but we don't know exactly why it happened. But yeah, we were pretty surprised because we expected exactly the opposite, more branch and bound, not less. Yeah. Which actually also brings me to a different point. We have a few nice sets of data, but one thing that I really would like to have, we have a few merchant donations, right? A bunch of people who would like their use of Bitcoin Core to work better gave us data and we're like, hey, can you use that to simulate? And if it works better for that, it'll work better for us. But what we don't have is a representative data source for a power user, like somebody that does a lot of that lives on Bitcoin, for example, or whatever.
That drug dealer.
Like that drug dealer, yeah. Well, so when yeah, I guess. I mean, just somebody that uses a lot of Bitcoin transactions and gives us a sequence of amounts and fee rates, so we could play it through from the perspective of that use case. As long as he doesn't tell me he is a drug dealer. And I don't know. Well, yes.
Wouldn't that dox the identity of the user? Because that's a big fingerprint right there.
Right, okay, so we actually have a script in Bitcoin Core that allows somebody to just dump their payment sequence, and it will fuzzify it by a few percent points, all the amounts, and it'll also fuzzify the fee rates, and that's the only two data. We don't collect the address or anything. And they generate it on their end and then can just give us those two sequences, or rather that one sequence of pairs.
Yeah.
So that's the other thing. We have fee rate sequences and we have payment sequences, but we don't have the combination of the two, which would be super interesting, because if we can see how and when they were actually crafting their urgent or not so urgent transactions, that would be a lot more accurate than our synthetic data that we have right now.
So this would be for a Bitcoin Core power user.
Somebody that has at least a few hundred payments in their Bitcoin Core, and yeah. If you happen to know somebody like that, a friend of yours or so, you could perhaps approach me later. All right, 15 more minutes. I'll have to pick up the pace a little. So this is a little bit of a pet project of mine. I've been working on this for a few years. And I've just come back to doing more of that in Bitcoin Core. So coming back to that transaction that I showed you early on with the 856 inputs at 46 satoshis per VByte. Well, Andy Chow, we checked out the 0.19 code base again to look back, because this happened in 2020. And we were very confused at the change output here, because the change output has 8,051 sats. And the minimum change in Bitcoin Core is 1,000,000 sats. So if it was optimizing for the smallest overshoot of the min change, how the heck did it come out to be 8,000 sats, which is significantly less than 1,000,000? So we looked at this, and we think that it must have had at least 2 iterations, and this is ancient software, which we've long improved since. But what it did was it didn't use the effective values of inputs, but after it picked the input set, it would have to account for the fees for the inputs. So effective values on inputs is you reduce the value of the input so that it has paid for itself at this fee rate. If you have a 1 millibitcoin input, which is, say, paid to public key hash, you deduct the cost of 148 bytes at the current fee rate from it, and that's the effective value. So when you pick that input, it has paid for itself already. Bitcoin Core didn't do that back then. So it picked probably some 600 or so inputs and targeted 1,000,000 change. And that change was not enough to pay for the fees. So it had to go again. It increased the target by the amount of fees that it had to pay for the 600 and something inputs it picked in the first round. So the target was now increased by 650 times whatever, that's wrapped SegWit, so 105 or whatever, some VBytes. And then it did it again, and it overshot just enough so it was able to pay for the fees. That 8,000 sats were left over after it paid for the fees. So yeah, okay, we can do better than this, okay? Use effective values when you do input selection.
So
yes?
Was this a merchant of sort, like a exchange, or?
Yeah, they have some automated business. They do deposits and withdrawals. I think they like a brokerage for buying Bitcoin.
This after it happened, and we're like, oh no.
Yeah, they were like, hey, we build a lot of transactions from Bitcoin Core. We get a lot of small deposits, and we saw this transaction at 46 satoshis per VByte with 800. So yeah. All right. So the conclusion here is obviously that the knapsack coin selection algorithm is crap, because it optimizes for the smallest change and not a good outcome for the user. And first we fixed that by adding the branch and bound algorithm, which looks for changeless solutions. But there is not always a changeless solution because it requires a specific combination of inputs. So if there's no changeless solution, we would still fall back to knapsack, and that would still happen. Then we introduced something called the waste metric, which I want to get into a little bit in the next slides, to have multiple algorithms create input sets and then pick the most opportune. And the step that I'm working on right now is get rid of knapsack and put some better algorithms in there. So hopefully this will never happen again. So what is this waste metric thing? Basically, our idea is, if I spend some inputs now, is it good or not in comparison to the long-term situation? So if the fee rates are very high right now, I probably want to use very few inputs. If the fee rates are very low right now and my wallet is all fragmented, I might want to use a few more inputs in order to condense the fund or compact the funds into fewer UTXOs going forth. So what the waste score calculates is the weight of the inputs times the current fee rate minus a hypothetical long-term fee rate. When I first implemented this, we used 10 satoshis per VByte. So the idea is, in the long future, when fee rates always go up, I'll still be able to consolidate at 10 sats per VByte. Now, looking at the last half year, that is maybe a little high, but it already improved the situation a lot. The excess is when we overshoot a little bit in a changeless solution, how much do we drop to the fees after paying for the transaction? And the change, of course, is if we don't get a changeless solution, it costs money to create a change right now, but it also costs money to spend that additional UTXO later. So we account for that in our metric. Is that kind of good? Cool. So we have a cost that's based on the current timing, the current fee rate, and how we build the transaction. Is there a change, or do we drop a little remainder to the fees? So I said already that 10 sats per VByte was not the optimal amount. So yeah, exactly. Because after June last year, before June last year, the mempool was constantly had a backlog, and then after that it was empty. So, sorry, should have put it a little higher up, huh? But yeah, so in the last half year, I think 10 sats per VByte as the consolidation fee rate is not the optimal pick. Yes?
Kind of depends on what your time scale is, though, right? Like long-term, 5 years, 10 cents per VByte might be too little.
Yeah, that we really would like to have a dynamic value for the long-term fee rate estimate, but we don't know how to calculate that yet. Originally, Bitcoin Core implemented it with the 1,000 block target, but that was just basically always 1. And then it didn't do any of the, hey, I want to be consolidatory in the low fee rate range, where fee rate range is less than the long-term fee rate estimate, which is always 1. So that didn't work optimally. And then putting it to 10 at least had us in the low fee rate range every once in a while when the fee rates were below the 10 sats per VByte. And then we would be consolidatory sometimes. However, for example, a befriended company told us they have more payments than deposits. That in the low fee rate environment that they had in the past half year, their wallet consolidated into like single-digit UTXOs all the time because the wallet would always be consolidatory, and then they basically have so little liquidity where they would almost have all their funds in flight and would reveal a lot about how much money they have in their wallet. So they didn't. They would like to have a larger UTXO pool. So there we would probably want to have a smaller target. So what did we do? Well, we just simulated it in our simulation framework with different values for the long-term fee rate estimate, from 1 sat per VByte to 10 sats per VByte on a fee rate sequence that looked kind of like the mempool did in the last half year, right? So an early on peak of fee rates, and then after that a lot of little noise between 10 and, I don't know, 15 or so. So what did we find out? Well, if you have a much lower long-term fee rate estimate, your UTXO pool is larger because you consolidate less often. And we see that especially here, up to 3 sats per vbyte, 4 sats per vbyte, the UTXO pool gets a lot larger. The second value that you see here, the red, is the percentage of transactions that were changeless. And that is neatly correlated. If you have a larger UTXO pool, you more often find combinations that don't require change. Right? So reminder, we're currently always using 10 sats per vbyte. So we only have slightly above 10% of changeless transactions for that. But if we had a lower long-term fee rate estimate, we might get changeless transactions up to 38%, at least in our simulation data, which might not be representative for everyone's use case. What else did we see? The algorithms that got used for each fee rate scenario, for each hypothetical long-term fee rate estimate, drastically changed. At low fee rates, we used BNB a lot more to find solutions and got changeless outputs. At high fee rates, we got a lot more knapsack solutions, which we want to get rid of, right? And the total cost that the wallet spent for the 5,000 payments was the lowest at 4 sats per vbyte. So this metric is both the fees that we spend for the 5,000 payments the wallet goes through, and then an estimated cost to empty the wallet, because every UTXO has to be spent at some point. So at least under the fee rate conditions of the last year or so, we probably want to be more on a long-term fee rate estimate of 5 than 10. And that also intuitively makes sense, because if you think about it, right now you can always get a transaction through at 1 sat per vbyte. So if you really have a fragmented wallet and you try to consolidate it, you would make transactions at 1 sat per vbyte to consolidate. And paying up to 10 times that in order to defragment your wallet seems like a pretty large range, right? So yeah, we're going to have a pull request soon. I'm going to run this on a couple of other fee rate scenarios. So if the fee rates are a lot higher, say more like, like this, where this is modeled after a daily sample from 2019 to 2020, where we picked one fee rate. I think it's the median fee rate for each day. So there we saw fee rates up to 200 or even up to 300. And then maybe a long-term fee rate estimate might be better if it were 10. And we are consolidatory, even if we're paying 10 times of what we might perceivably get through at some point, we would still save a lot by not spending those UTXOs at very high fee rates. All right. I think I'm not going to get through all of this. Yes, thank you. I want to do this one still. So recently, Bitcoin Core changed its behavior for change outputs. When we send to a different output type than what our wallet by default uses, we're going to match it. And why would we do that? Well, if you're spending wrapped SegWit inputs and you send to a legacy output and a wrapped SegWit output, which one will be the change?
Legacy, just because I think it's a trick question.
Right. OK, it's not a trick question. Obviously, the same input type, or if all your inputs are wrapped SegWit and your output, one of them is wrapped SegWit, one is an older, less efficient format, then probably the change output is the more efficient one, right? Because if you were sending to yourself, you wouldn't want to spend more on spending that UTXO later. So we've revealed which one is the change output and which one is the recipient output. Yes?
When you go through these exercises, do you assume that you have rational users? Because, like, for example, some elect to use the blockchain wallet as opposed to something better, like not blockchain wallet.
Well, even blockchain.com now uses native SegWit since last June, actually, which was probably one of the reasons why we've seen so little block space demand. Yeah. Pretty amazing.
I'm curious if I could ask a question. So if you go into a legacy address with a change to match that, when you go to spend that change later, does that logic change too? What do you do there?
Exactly, right. So now we'll match the output. So we're sending to a legacy output, and we also create a legacy change output. But then in the next transaction, we use wrapped inputs and legacy inputs. So probably we could have also received a wrapped input, also reveals that ours was the change and not the receiver. So Josie had the idea, why don't we just try to spend all output types separately? So if we have a bunch of legacy outputs, a bunch of wrapped outputs, a bunch of native SegWit outputs, we just first tried to do coin selection on just one set of these. And he simulated that, and he did 125,000 payments, 13 of those mixed inputs. So he was always able to create an input set that only used a single type. And so that's pull request 24584. And that works surprisingly well, and it reduces the overall cost of the wallet too.
Can you repeat the idea? So it's specifically the idea that the wallet should only ever spend the same output type as the recipient.
So there's
which means you should never consolidate UTXOs of different types either.
Correct. So a lot of wallets only allow a single type. And to basically hide among them, if we also only spend a single type, we'll have less of a fingerprint. Spending multiple types together is a fingerprint. And the funny thing is, in combination with our waste metric, because the weight of the inputs is different for different output types, right? A paid-to-public key hash, a legacy input, is 148 vbytes. A native SegWit single sig version 0 input, paid-to-witness public key hash, is 68. So it's almost half. So if we have a set of inputs with the same count from either of those, at high fee rates, we'll prefer the small UTXOs, the more modern block space efficient UTXOs. And at low fee rates, we'll prefer the old legacy inefficient ones. So we actually move a lot of our transaction costs to low fee rates that way. And I think that's the reason why Josie's pull request actually reduced the cost by almost 10%. All right, I think I'm over, right? If you want to learn more about all that stuff, you should come to our PR review clubs. We had a bunch of these on lately. And there's a bunch of fun stuff going on in the wallet right now. We have 6 or 7 people working on this pretty actively lately. And if you want ideas or feedback on your own wallet that you're working on, or other things from my wish list, then please feel free to talk to me. Thanks.